Now we're going to continue to look at section 5.5, zeros of polynomials. We can now look at real zeros and complex zeros. So we want to find all zeros of the given polynomial function, but this time we're not going to be given a zero or a factor, and it's not factorable. So we know how to find zeros of a polynomial. We set the function equal to 0 and solve for x. Okay, now like I said, this is not factorable, so we're not going to be able to just directly solve that for x like we maybe have in the past, and we don't have a zero or a factor given to us. So we need another tool, and that tool is the rational zero theorem. And don't be thrown off by that word theorem, it's pretty basic. All rational zeros of a polynomial function are of the form x equal to p over q, where p is a factor of the constant term. All right, so up here we have constant term of -10, and q is a factor of the leading coefficient, and our leading coefficient for our example up here is 1. Now, one thing to note, when the leading coefficient is 1, like we have in our example, the possible rational zeros are the factors of just the constant term. So let's use that to find possible rational zeros of this polynomial function. So that says that our possible rational zeros are equal to factors of -10. Okay, so let's list out factors of -10. Well, we could have 1 times -10, right? And we could also have -1 times +10. So we're going to include plus or minus 1, plus or minus 10. We could also have 2 times 5, or -5, and we could also have -2 times +5. So in each case, we're going to get a plus or minus for each of our factors. Okay, so we have 8 possible factors. So 8 possible, and I should actually say possible zeros of our function f of x. Now, that doesn't mean all 8 of those are going to be zeros. In fact, not all 8 of them are going to be zeros. We need to test using synthetic division to see which ones give us that remainder of 0. Okay, so here's our setup for synthetic division, and we want to test out these different possible rational zeros to see which ones are going to give us that remainder of 0. So let's fill in our coefficients, and now we're just going to choose one of those possible rational zeros. So let's just choose plus 1, and we'll go through the process. And it turns out that first time we get remainder equal to 0, so that means that f of 1 equals 0. All right, so we've figured out that one of our rational zeros is 1. So 1 is a 0 of this function. It's a real 0, which also tells us that x minus 1 is a factor. So if we start to write the factored form of the polynomial function, we get f of x equals x minus 1 times the polynomial with the coefficients that we have to the left of 0. So remember, this other factor is going to have 1 less degree than our original, so it's going to be degree 3. So we get 1x cubed plus 4x squared plus 9x plus 10. That's going to be our other factor. X cubed plus 4x squared plus 9x plus 10. Okay, now we need to figure out the zeros of this other factor. All right, so we look at our constant term. Our possible rational zeros are going to be factors of 10. Well, that's the same list that we have up here. Okay, so we are going to run through synthetic division again, testing out another one of those values. All right, but this time we're going to use the coefficients from this other factor. So we get 1, 4, 9, 10. And let's test out 2. So let's bring down the 1, multiply. We get 6, multiply, we get 12, add down, we get 21. 2 times 21, we get 42. And we add that down, we get 52. And that definitely is not equal to 0. So that tells us that 2 is not a 0 of this function. All right, so we tried out 2. That didn't work. Let's just keep trying. And why don't we try out a -2. Now, you notice I'm not trying the bigger numbers, and my experience is that usually it's not the bigger factors like the 5 or the 10. Sometimes, but a lot of times it's not. Okay, so bring down the 1, multiply, add down, multiply, add down, and then multiply, and we get another 0. So that is a remainder of 0. So that tells us that f of -2 equals 0. So -2 is a 0 of this function, and that tells us that x plus 2 is a factor of the function. So we can now write down a more factored form. We get f of x equals x minus 1, x plus 2, and then now our other factor is the factor that we get with these other coefficients. Reducing the degree by 1, we get x squared plus 2x plus 5. So our other factor is x squared plus 2x plus 5. Okay, so now it is down to this quadratic. We need to find the zeros of this quadratic. So we set that equal to 0 and try to factor. And we're not going to find values that multiply to 5 and add to positive 2. So it doesn't factor. That gives us our method of quadratic formula. So we get x equals -2 plus or minus square root 2 squared, which is 4, minus 4 times a, which is 1, times c, which is 5. So we get minus 20 all over 2 times 1. Okay, so we get x equals -2 plus or minus. We're going to end up with a -16 underneath that square root. That's all over 2. We want to simplify, but we now know what to do here with that negative under the square root. We can bring that negative square root, we can bring out the square root of -1 is I, and then we have square root 16, which that will simplify as well. So -2 plus or minus 4i over 2. And then continuing to simplify that, we get -2 over 2 plus or minus 4i over 2. We've got some common factors. -2 over 2 is just a -1, plus or minus 4 over 2 is 2, so we get -1 plus or minus 2i. So we have 2 complex solutions in addition to the 2 real solutions that we found, 1 and -2. So that would be the answer to this problem where you're asked to find the zeros of the polynomial. Let's look at this example. We want to find all zeros of the polynomial function, and again, we're not given a 0 and it's not factorable. So we want to remember if the leading coefficient of our polynomial is 1, then the possible rational zeros are factors of the constant term. So we can list out our possible rational zeros by taking the factors of 8. So factors of 8 are plus or minus 1, plus or minus 8, plus or minus 2, plus or minus 4. All right, so we have a list of 8 to try out using synthetic division. So here's the setup. I've got the coefficients listed there. Let's pick one of those possible rational zeros to try. And let's just start with 1. Bring down the 1, multiply, add down, multiply, add down, multiply, add down, multiply, and when we finally add down, we get 0. So that tells us that 1 is a 0 because f of 1 equals 0. That means x minus 1 is a factor, and the other factor has the coefficients that are listed here, 1, 3, negative 6, negative 8. Okay, so that's the factor that we're going to have to do synthetic division on again. So the cool thing is we're not going to have to rewrite everything. So we can just set this up doing synthetic division with those coefficients. Our constant term now is negative 8. Well, we get the same possible rational zeros for negative 8 as we did for positive 8. So we can pick from that list another possible rational zero to try out. So why don't we go ahead and give negative 1 a try. So bring down the leading coefficient of 1, multiply, add down, multiply, add down, multiply negative 1 times negative 8, we get positive 8. We add down and get 0. That means we found another 0. F of negative 1 equals 0. So far we have x equal to negative 1 and x equal to 1 are zeros. Now we have got the factored form of our polynomial based on those two zeros, x plus 1, x minus 1, and then our other factor is going to be 1x squared plus 2x minus 8. So x squared plus 2x minus 8. So we just have to focus on that quadratic now and set that equal to 0. See if we can factor that or use quadratic formula to solve for x. Well, we're going to be able to factor this one. X and the two numbers that multiply to negative 8 and add to a positive 2 are x plus 4, x minus 2. We set those equal to 0. We're going to get x equal to negative 4, x equal to 2, and then adding on to our list the zeros that we already found. That gives us our full list of zeros for that polynomial. Another example, we want to find the zeros of the polynomial function. Again, no zero is given. It's not factorable. We want to list out the possible rational zeros to start off with. And because our leading coefficient is 1, it is going to be factors of the constant, which is negative 26. So we're going to have a list here. Plus or minus 1, plus or minus 26, plus or minus 2, and plus or minus 13. And I think that's it. So we need to test out which ones are actual zeros. Let's list out the coefficients, 1, negative 8, 25, and negative 26. And let's choose one of those values to start off with. Let's try 1. Bring down the 1, multiply, add down, multiply, add down, multiply, and when we add down, we get 8, negative 8, which is not equal to 0. So our remainder not equaling 0 means that 1 is not a 0 of the polynomial. Let's try 2. All right, well, it's going to look like that 2 will work out, and we get that remainder of 0. So 2 is a 0 of the polynomial. So we can write our polynomial as the factor that comes from 2, which is x minus 2, times the other factor, which is going to be quadratic because we started off with degree 3, so 1x squared minus 6x plus 13. So we want to now solve for the other zeros by taking that other factor, setting it equal to 0, and solving for x. It's a quadratic, and we've got a couple choices or couple possibilities. We can try to factor it, or we can use quadratic formula. Well, we're not going to find values that multiply to 13 and negative 6. We're not going to find integers that multiply to 13 and add to negative 6. So we use the quadratic formula. So negative 6 plus or minus 6 squared underneath the square root, negative 6 squared, which is 36, minus 4 times a, which is 1, times c, which is 13. 4 times 13 is 52, all over 2 times 1, which is 2. So simplifying, we get 6 plus or minus square root of negative 16. So we're going to have some complex zeros, not real. Let's just keep simplifying this. 6 plus or minus, well, square root of negative 16, we can write the square root of negative 1 as I, and square root of 16 is 4. So that simplifies to 4i. And now breaking those up into the real part and the imaginary part. All right, we've got these two separate terms, 6 over 2 plus or minus 4i over 2. And simplifying those, 6 over 2, we get the real part is 3. And simplifying 4 over 2, which is 2, so we get the imaginary part is 2i. So our full list of zeros then is x equals 3 plus or minus 2i. So that's two separate complex solutions. And then the other solutions are, or the other solution is 2. The other zero is 2.